keynotes. Western Digital's keynote co-presenters are Dr. Luca Fasoli and Khurram Ismail. Dr. Luca Fasoli is Senior Vice President of Silicon Technology and Manufacturing at Western Digital. He is responsible for the strategy and the development of Western Digital solid-state memory technologies. Previously, he held engineering management positions at Wafer Scale Integration, ST Microelectronics, Matrix Semiconductor, and at SanDisk after its acquisition of Matrix. As a 25-year industry veteran and IEEE senior member, Dr. Fasoli has worked on a variety of non-volatile memory technologies and solid-state storage products, leading product development teams from concept definition to mass production. Dr. Fasoli has published many technical papers and holds more than 90 US patents. He earned a doctorate and master's degree in electronic engineering from the Polytechnic University of Milan and completed the Engineering Leadership Professional Program at UC Berkeley. He is based at the company's Milpitas, California location. Khurram Ismail is Senior Vice President of Engineering for Western Digital's Flash Business Unit. In this role, Ismail oversees product development of the Flash Business Unit's growing portfolio of SSDs, embedded, retail, consumer, and removable products. He leads a multidisciplinary team, product development, including ASIC, firmware, hardware, validation, and system design engineers who are focused on vertically integrating Western Digital Flash technology with engineering solutions to serve a wide range of customers, from OEMs to consumers. Ismail brings 22 years of engineering and management experience in the flash industry with a unique combination of business acumen, technical understanding, and systems development gained as an engineer and executive at companies including Western Digital, SanDisk, and Micron. His prior roles include product development in client and embedded applications engineering, supporting DRAM, flash, and product and test engineering. Ismail earned a bachelor's in electrical engineering from Northern Arizona University. Khurram Ismail is based at the company's San Jose, California headquarters. Please welcome to the stage Dr. Luca Fasoli and Khurram Ismail.
Testing. Oh, thank you. Good morning, everybody. How can you follow Eli? I don't know, and be successful is absolutely impossible, but may the force be with you, Eli. Before I start, let me point out to the forward-looking statement, which basically is saying, whatever I say today, I can change my mind at any time, and I don't need to come back and tell you. And this kind of gets me out of trouble. So now that the lawyers are satisfied, let me go into the talk. So we're here to speak about the past, the present, and future of NAND through the eyes of Western Digital, through our own eyes. But before I do that, I want to kind of ask you a question. So you've been scrolling your news feed, you're looking it up, you go down a rabbit hole, start scrolling around, and all of a sudden you find yourself watching tens of or 20 of different cat videos. Now, the question that normal people ask is, how in the world are we going to survive yet another video? But, you know, we're engineers, we work in storage, and the question we normally ask is actually, how in the world are we going to store them? And this seems to be like an artificial question, but it is not, actually. The quantity of data that gets created every day is vastly above the data that actually gets stored. So you can see here, we're going to be creating 200 zettabyte of data by 2026, and we're only really storing around 7% of it, at least in 2023. And this, not that we need to store all of the data that we create, but there is data that, if stored and processed in the right way, can help us solve some of the problems that we're facing in the future. So what I'm here to discuss about is how we're going to close this gap. And specifically, I am going to speak about NAND scaling and some of the NAND technology design innovation that we are doing to close the gap between application and the NAND technology. And then Khurram is going to come in and speak about and tell you how do we get into the zettabyte era, what does it mean to be in the zettabyte era, and what type of product development strategy we need to implement to satisfy the need of the zettabyte era. So let's dive into it. So this is a pretty simple graph. It shows you the memory hierarchy, the various layers, and right there, smack in the middle, you have our core technology, NAND flash. That is really key, and today it plays already a key part in the technology. Having said that, we see that technology through innovation, performance improvements, and cost improvement to actually expand in the future. And really will expand up, down, and sideways, and really be able to go up into the memory space and go down in the storage space. So we believe it is the most exciting technology out there in the semiconductor space, and it's going to play a crucial role for the future. Now, we believe that there's quite a bit of things exciting happening in HDD as well as part of Western Digital, but again, I'm not here to speak about that in this conference. I'll leave it for somebody else in some other conference to discuss that. So hit me up if you want to know where. All right, what is the core technology? What is the heart of the 3D flash technology? Is the charge trap device. The inventor was just recognized it a few minutes above, and this device is simple, it stores a bit, and it is the most produced semiconductor device bar none. We produce more charge trap device than any transistor, any passive that you might have. We actually produce in a year more charge trap device than there are grain of sand in all of the beaches in the world. So it is absolutely the most produced semiconductor device of all time. Having said that, it's not that we produce it the same way. We actually keep improving it. And over the course of, for example, from the beginning of the 3D NAND revolution to now, we are actually been improving the performance by 20% generation over generation. And to make a fine point on it, I want to share with you one graph. 2D NAND has fueled the flash revolution for the first 20, 25 years of flash. And the best device that we have, the 50 nanometer device, 3-bit per cell device, is now surpassed in terms of performance by a 4-bit per cell device in 3D NAND. So this is how better the device has become. Now, how do we put the device together and build and produce and scale up? We just basically build taller devices. We put more charge trap devices on top of each other, and so we increase the memory density within the silicon area. And how do we do that? We do really by 4 different vectors. The first vector is vertical scaling, and you just don't want to scale vertically. You want to be able to do it smartly, so you have to implement innovation that allows you to do it effectively. So, for example, you build the stack into multiple steps, for example, with 2, 3, 4, or more. You also want to make sure that the stack is as small as possible, and so you want to make those memory layers as thin as possible. Now, you want to do that smartly. You don't want to degrade the characteristic of the device. You don't want to degrade the performance, so you have to do new material techniques and process techniques so that you could do it. This is the most straightforward way to do it, and this is what gets publicized in the industry. But in reality, there are another level of scaling, which is the lateral scaling. And lateral scaling is absolutely necessary, as I'll show in the second slide, and it means about scaling the X and Y. It was the only scaling available in 2D technology, and it has to happen in 3D technology as well, and it's somehow hidden. And it happens through increasing the memory density and also trying to remove some of the overhead and amortize it over a larger number of cells. That overhead is needed because you want to be able to electrically access all of the cells in the various memory stack layers. The third level of scaling is what we call architectural scaling. These provide quantum jump generation from multiple generations. And we started building the NAND technology using exactly the same type of architecture that we have in 2D, which is the circuit to read the memory array is actually on the side. And then we started believing that you can tuck CMOS under the array as well. This is a technology that was pioneered by Matrix Semiconductor in the early 2000s and became useful for now in 3D NAND. And in the future, we believe there's going to be further opportunity for scaling laterally. Scaling is the scaling that the 3 people just recognized started, is the logical scaling. Logical scaling means you go from 2-bit per cell, 3-bit per cell, 4-bit per cell, etc. We believe it's possible to go to 5-bit and beyond. It requires really 3 critical pieces. The first one, you need to have a solid charge trap device that can allocate all of the levels that you need. You need 32 levels to 32 independent levels for 5-bit per cell. You also want to be able to read it at the system level. So you need to have the error correction techniques. You have to need the system improvement to allow us to program them and read them reliably. And lastly, you need to match the application to the performance. As you can imagine, going from fewer bit per cell to higher bit per cell, read and program performance are degrading, and so you need to really find the application that you need to match it up. So these are the 3 key elements to enable multi-bit per cell. Let me now go back and kind of show to you why we believe lateral scaling is extremely important. If you just were to blindly scale vertically, you actually reach a level of diminishing return for a couple of reasons. The first reason is because in order to percentage decrease the cost or and increase the memory density, you need to, in percentage, add the same number of layers. So the absolute number of layers that you need to add generation from generation is actually growing. And so it becomes increasingly complicated. The second is that adding more layers requires more tools and more time to process those layers. And so your capital goes up. The capital that you need to put in the fab actually goes up. And so there is a diminishing return to adding more layers. So what you need to couple vertical scaling with lateral scaling in a smart way. And this is in 6th generation, Western Digital will achieve 30% better cost with lateral scaling than if we had without it. And again, you achieve that by reducing the overhead and increasing the memory density. And I want to speak a little bit about tool and requirements. One of the situation that's happening in the NAND industry is that as you add more tool, your capital, you need to increase the capital that you put in the fab. And it's actually reducing the capital efficiency. So the amount of capital that you need to increase the bit supply by 1% is increasing. So this is a problem. But the solution is really to be very smart about the capital investment. And as a matter of fact, when you look at different NAND vendors, they have approached this problem differently. I'm now showing the CapEx that's needed per incremental bit across 5 different vendors. And you can see there are different ways to develop technology that over the 2 years, from 2020 to 2022, has provided different capital efficiency. And so it's really important as you think about new technology development to think about the capital that you're going to need to generate the additional incremental bit. And now that I've spoken about kind of all of the ingredients, I kind of want to give you a little bit of our view of the long-term roadmap. So first of all, we believe that NAND is here to stay for a very, very long time. There is no fundamental physical limit to scaling NAND. It's just a manufacturing problem. And so we need ingenuity to manufacture reliably this device. As we started in 2D with the first viable BICS technology, we then went to 2 tiers. We are now in the midst of the transformation, trying to squeeze X and Y through lateral scaling and with the circuit under the array. And then we see for the future to enable 500 layers and plus other innovations that are coming, 5-bit per cell of memory density increase and multi-tier stacking. One thing I want to speak about, CMOS scaling is also becoming extremely important. As your memory has to be matched to the array if you build a circuit under the array technology, it is important that array scales correspondingly if you don't want to increase the density of a single die correspondingly. So this is a fine point. So this is kind of our view of the long-term memory NAND roadmap. Let me now switch gear a little bit and speak a little bit about some of the design innovation that we've implemented to try to close the gap between application and NAND technology, fundamental NAND technology, because you need to do that as well. The first one is with respect to how do you get the data out, and random read is one of the key metrics in many of the enterprise applications. And normally, you would actually take the NAND memory array, divide it up into multiple chunks being plain that you can read from. Now, normally you would do that synchronously. But through circuit innovation and device innovation, we have made those playing independently. And all of a sudden, the reads can happen kind of randomly at all planets. And that intuitively improved the random read performance at the system level. As a matter of fact, if you have a two-plane device and you go from synchronous read to asynchronous read, you get a 32 better performance for random read. And if you have a four-plane device, you add that, you actually increase by 82%. And these allow us to satisfy the need of some of the random read requirement application. The other need is how do you squeeze the data out from this even larger memory array? You have a host I/O interface that continues to increase with the PCIe, following the PCIe roadmap. And then you have a back-end interface from the ASIC to the NAND. That yes, it has multiple channels, but you still need to take out the data from the back-end at the same speed of the PCIe. And so it's important that NAND I/O interface also scales up at the same way. And the industry, and we at Western Digital have been able to deliver 30% node over node performance improvement in the I/O speed. And let me now go back a little bit to bit per cell. And normally we think about bit per cell in a discrete fashion, 1 bit, 2 bit, 3 bit, 4 bit, 5 bit. It doesn't need to be this way. You can actually devise systems that are able to extract half a bit more than 3 bit or half a bit more than 4 bit. And that requires a careful design of the NAND device and of the system to be able to extract those additionally half a bit from the technology. And that can provide very specific solution to application that might be right in between 3 and 4 bits. So for example, a 3.5 bit technology could be satisfied for a cost-optimized performance SSD, or a 4.5 bit per cell ahead of 5 bit per cell enablement can provide cold storage for the application. Let me close my portion by discussing a little bit the architectural trade-off that we go through as we think about newer NAND technology NAND. These are only 2 examples. These are not the only one, but I just want to give you a sense on how we think about it. So the first discussion that happens, what is the die portfolio that you pick? And as you define a technology, you can build smaller dies or larger die as long as the technology enables you to do it. And as you pick the die to build the product, you need to be extremely careful on what is the right die sizes, because there's a clear compromise between having smaller density and having higher performance product versus having larger density, using larger density die that has that has lower performance but better cost. So that's a trade-off that you need to consider. The second trade-off that you need to consider on top of the trade-off is how do you pick your technology. And so, for example, as I discussed before, you have some freedom in what is the thickness of the layer that you use for NAND. And you can make it thinner or you can make it taller. And if you make them thinner, there's more cell-to-cell interference. And so you get a worse performance, but you get a better cost because the stack that you need to etch to produce the memory is smaller. And that's one trade-off that you need to play. So as we design new technology node, we continuously look at these 3 vectors, performance, endurance, CapEx, and then we try to make sure that we provide the best performance and endurance within the constraint of capital efficient, which is extremely important. Let me stop here. I'm going to ask Khurram to come on site. But before I do that, I want to share a video that we have prepared to celebrate the 35 years of NAND.
Thanks, Luca. As I was walking up, I was reminded by Chuck that I'm the last person standing between you and lunch. So I'll try to bring it home on time. Great video. Goes to show how we as an industry have come a long way in enabling so many exciting applications and use cases. But we are just getting started. Luca talked about the innovation that took place over the last 35 years, the technological advancements, and where we are headed over the next few decades. I want to complement that a little bit with the market and segment view, provide you a little bit of perspective on how market has adopted all those advancements, and what might we do on the product development strategy as we move into the zettabyte era. So it all started with the petabyte revolution. Sorry. It all started with the petabyte revolution, where the consumer applications like card, USB, and SD enabled the petabyte and the consumption of the NAND flash. Now, there was a lot of progression in the ecosystem with respect to new interfaces being announced, like UFS, eMMC, NVMe. There was a lot of innovation in the form factor that enabled markets like mobile, compute, hyperscale, and enterprise, which brings us to the point here we are today. And we are at an interesting point in time between this year and the next year. We're going to be transitioning from exabyte to the zettabyte era. And we don't see slowdown from there. We see 30% CAGR year over year for the next 5 years in the zettabyte era. Now, what are some of the emerging trends? What are some of the markets that are going to support that scale? I want to talk a little bit about that. But before I do that, I want to just talk about zettabyte scale. The scale of zettabyte is so huge, it's like a sold-out Levi's Stadium with spectators watching 4 football games for 80 years. Another way to think about this is every human on the planet watching a 4K footage for 3 hours. That's the scale that we are talking about. Now, let's dive into some of the segments and some of the trends that are driving this growth. The first one is enterprise. It's been talked a lot about that cloud is the fastest growing segment with double digits CAGR over the next 5 to 10 years. And we don't see a slowdown. The flexibility that the cloud platform provides and the provisioning it provides for so many use cases, we don't see a slowdown. One example, among many examples, is the smart building. A smart building with various endpoints generates about 50 terabytes of data per day. Now, that data needs to be stored, needs to be processed, and that's where the cloud comes in. That is just one use case. Imagine the possibilities with all the new applications that'll drive the cloud. The next segment is automotive. Automotive is also one of the fastest growing segments. And automotive is not only growing in terms of petabytes, exabytes, but it's also growing in size and volumes. Now, the traditional automotive segment is driven by the black box, by the navigation, by maps. And what we are seeing now is a new trend that is emerging, which is the autonomous driving vehicles. Now, the autonomous driving vehicles are interesting because there's a lot of sensor data that gets generated as part of the autonomous driving. Now, that data, given the amount of sensors that you have in the car, can generate anywhere from 1.4 terabyte per hour to 19 terabyte per hour. Again, not only it will require a local storage, but also a cloud server to process that data, to provide autonomous driving enhancements, improvements, and analytics. And here's a stack of the storage hierarchy in that autonomous driving vehicle per day, or the next decade. And as you can see, the sensory data is at top of the heap with 1 to 5 terabytes, followed by the normal use case of automotive. This one is my personally favorite, the gaming. For those of us who played the first Call of Duty game, it used to take 1.5 gig to install on the PC with the storage requirement. With the latest version of Modern Warfare, it takes about 175 gig. 100x increase over the last few years. And then not only the average game size is increasing, but also the capacity on the gaming is also increasing for the drives. Today, we are at 512 to 1 tera, moving to 2.5 tera over the next few years. So these are exciting times in Flash. We don't see any slowdown. One of the trends that powered the exabyte was the need for higher capacity and performance. But what we are seeing with these trends is not only for the need for higher capacity, but fast and consistent data. So now how do we adjust our product development as we move into the zettabyte era? Now, one of the traditional approaches have been, on the development side, is you develop for each swim lane. As the ecosystem progressed, as there are new standards that were introduced, we took the approach of designing for those standards, for those customer requirements, for those verticals separately. This worked out great, supported the revolution that we were in, but it also had a little bit of flip side, which is minimal commonality between product lines and segments, unique architecture per product, and it could provision a decent, moderate progression in ecosystem. Like I said, this dedicated development approach gave us the agility, allowed us to serve the markets, allowed us to serve the scale that we were in. But what about now? As we are going to the next level, as we are going into the zettabyte era, could we use this product development strategy and succeed moving forward? So I want to draw your attention to client SSD platform-based approach that we took at Western Digital. Now, client SSD was one of the fastest evolving segment over the last 5 to 10 years, naturally displacing HDD in laptop, desktop applications. Now, when we were going to develop for client SSD, the traditional approach would have been that we would develop a product, a design for performance, mainstream, value, and non-PC swim lanes. Those are the predominant swim lanes in client segment. Instead, we took a very holistic approach. We took a platform approach where all the NAND customizations, where all the ASIC IPs for back-end, front-end, ecosystem progressions, all the validation infrastructure and debug, we encapsulated it all in one platform. And through that, we iterated all the customization, the need requirements that came in. An example of that, the WDC 4-channel, 8-channel, DRAM, DRAM-LAS were all encapsulated and thought through in this platform approach. The result, leadership in client segment, as well as very fast development in product life cycle. Now, as we are going through the zettabyte era, I talked about a lot of new markets that are emerging. How do we change our platform-based development approach? Should we scale on top of client SSD, what we did in client SSD, or should we keep the traditional approach? Well, the answer is we have to think about it. We have to have a true one architectural North Star. And that architectural North Star has to provision for all the enhancements that are going to happen in BICS technology, has to think through, contemplate all the changes that will happen in ecosystem from customer's point of view, and will drive the faster time to market, lower cost, high quality, and the ability to serve the full portfolio. We believe this is the direction that we got to head to. I don't know if Ellie is here in the room, but the secret sauce is alive and well, and we believe that this is the way to go. Now, with this strategy, we already see with the same amount of resources and time, we are able to develop 2x more products. So Luca and I talked a lot about many things. If you want to walk away with one message, this will be on the next slide, which is my last slide. So the star of NAND flash is burning as bright as ever. We don't see any end in sight. We talked about the charge trap cell at the center of this revolution, powering the growth into the next few decades. All the innovations that Luca talked about, be lateral, architectural, and logical and vertical, those will all provide us a very, very long runway as an industry to survive, thrive. And then with the secret sauce, the co-optimization, the vertical integration that we have, and with the architectural North Star, with one true platform serving the entire portfolio, will help us get into the zettabyte era. Thank you.